Today we're going to be covering lesson 2.6, which honestly is really just more proofs. In this lesson, if you look at it in the book, they really would like you to start to go over flowcharts. But again, I've done enough math that I can tell you that nobody cares what format you use when you complete a proof. And even through college, it's actually more common to see a 2-column proof than it is a flowchart. So we're just going to stick with 2-column plus because I already had to pre-type these up. I couldn't really ask you what you guys wanted. So the only thing that's different today is they just add on 2 additional one postulate, one theorem, but you kind of already know the first one. It's more just the second one. So they add on these 2 pieces, and then really it's just giving you more practice. But these problems today look just like they did in 2.5, okay? So first, you guys already know what linear pair is. But today in this lesson, they kind of just add on the word postulate, but we've kind of already been working with this, even though now it's sort of formally defined. So when you hear the word linear pair postulate, you're basically saying that not only are the 2 angles adjacent, and not only do they fall on a straight line, but now they add up to 180. So that's kind of how the linear pair postulate works. Now, I'm going to skip this second one for just a minute and let's go down to this proof and you'll kind of see it in the proof here, okay? So, as we've seen yesterday in yesterday's lesson, we're going to recopy the given in spot 1. Now, we can drop the little m's. Those are not that important. That just means measurement. So we're just saying that angle 1 plus angle 2 is equal to 4. So if you look, 1 plus 2. Now we don't know what those measurements are. Maybe they're the same, maybe they're not, but we know that together their total will equal 4. So we say that's given. And now we look at the hint, and the hint says linear pair postulate. So when you look through this picture, there's only one location where linear pairs exist, and it's right there. So what we're going to want to do is we're going to want to put those together. So angle 3 plus angle 4 is equal to 180 degrees. And again, that's due to this postulate. Now we know the last line is right here, so we know that's going to come down. So I'm going to copy that, and again, I'm just going to drop the little m, sorry. I was writing a 1 and said it. So I'm dropping the little m's. But remember, we're not allowed to put the word prove here. We actually have to come up with a reason how we get there. And I know you can probably guess, but I want you to think inductively. We learned that earlier in this chapter. So the 3 is coming down. The 180 is coming down, but do you notice they're getting rid of this 4 and putting something in its place? So they're taking this out and they're replacing it. And so once again, you see good old substitution. So substitution, again, is the most commonly used property that we pretty much have in geometry, okay? Now, again, you don't have to use it, but it is really, really common. Now, before we move to the next page, which there's just a bunch more examples for you to try, is this next theorem. So notice we have a postulate, which is something we assume to be true. Like if this is a straight line, then don't they have to add to 180 because it's a straight line? Like we assume it to be true. Whereas a theorem is something that can be proven. So if you want to take a look in your book, I don't remember exactly what page, but they actually go through the formal steps of this in your book. But basically what I want you to kind of think about is like, let's just take an example. Like let's say you have a line, okay, so you have a line and then you have a picture like this, and let's say this is 90 and then let's say this is 90. So we'll just call this for easy sake angle 1 and angle 2, okay? So let's say that you are given angle 1 is a right, angle 1, how about we say and angle 2 are right angles. And they want you to prove that they're equal or congruent to each other, okay? Now, our brain kind of automatically jumps from here to here. It interprets this word and we just automatically kind of jump, go from one conclusion to the next. But that you're not allowed to do that in proofs. I mean, if you think about a manual of a toy, if you buy a toy, I guarantee somewhere in that manual, it probably tells you to insert batteries. Well, duh, doesn't everybody know that? But they still have to put it in their manual. So let's say I've got my given, and just for time's sake, I'm not going to recopy it. So 1 and 2 are right. Now, if you're thinking to yourself the definition of right angles, that tells you that they're 90 degrees. It does not tell you that they're equal to each other. So you would need to say angle 1 is equal to 90 and angle 2 is equal to 90 based on the definition, because that's what the definition says. Now, because they're both equal to 90, they both have the same number here. Now we could say that they're equal to each other or congruent to each other. And that is basically using substitution, or if you want to call it transitive. I almost put subtraction. Substitution. Okay? Because what we're doing is we're essentially taking out like the 90, we're getting rid of this and we're putting this in its place. Otherwise, if you try to eliminate this second step, so if you try to get rid of this second step, how are you going to prove that they're equal? Like, what justification are you going to put here? Because definition of 90 does not tell you they're equal to each other. It tells you they're equal to 90. So you would kind of need the steps. So the theorem that they're giving you here, it's called the right angle congruence theorem, essentially is allowing you to skip one step. It's allowing you to say, if they're both right, then they must be equal. So this exact same proof, if I was to do this exact same proof with the new theorem, I would do my given, so that would be pretty, recopy given, and I would be able to jump right to the prove statement, and I would be able to say right angle congruence theorem. Now, don't abbreviate this too much because RACT, that's not a universal abbreviation. So don't start making up your own abbreviations or you might get in trouble or get stuck. But this new theorem kind of allows you to skip over the definition piece. So it's just kind of being a little bit more specific. And that's really what a theorem does. A theorem is just really gets into the nitty-gritty details of some of these vocabulary words or images, things like that. So I would say this is a fairly commonly used property. I mean, both of these two that I've highlighted here, I would say you use them a fair amount. They really do get used a fair amount. So, know them, practice them, kind of put them on your page if that's what you're working with, like an additional, page or list of topics that you're going to need them. Now, if you notice, there are, I believe, 3 more proofs, and then there's just 2 algebraic problems. So there's numbers 2, 3, and then there's 1 more on the other page, okay? So at any given time, you have a pause button. I would think it would be to your benefit to pause the video, try it on your own, and then hit play, okay? So at any time, you can do that. All right, I'm going to recopy my given. I'm going to kind of just mark this. So 2 is congruent to 4, and then they want me to prove that angle 1 is congruent to 3. Like that's what I'm going for here. All right, so if I look at their hint, now remember, in this chapter, we're giving you the number of steps and we're giving you some occasional hints. But when we see proofs in another chapter, they're going to be blank and you're going to have to do them on your own. So in this particular one, we have 1 plus 2 equals 180 and 3 plus 4 is equal to 180. Well, what I'm noticing is that these are both linear pairs. So linear pair postulate. Now, if you forget the P or you exit the last P, or if you put a T for theorem, I would give it to you, okay? That's just kind of being really, really specific. All right, now they're telling us it's substitution. So when I'm looking at this for substitution, something has to be repeated. So if you notice, the 180 is the exact same thing. So I'm going to get rid of the 180, and it doesn't really matter if you get rid of the top or the bottom, but then you're going to put these two together. Okay, now I'm going to keep the 2, the one that has the 2 on the left since it's here, and the one that has the 4 on the right since it's there. What I'm saying is it doesn't matter really which side the left and the right is, but I'm just going to try to kind of keep it so it matches my first statement. So I'm going to say 1 plus 2 is equal to 3 plus 4. And again, they just did substitution. Now we know what the last line is. We know it's 1 to 3. And again, we can drop the little m's, but we have to figure out this justification. Now, substitution can be used more than once. It's not, I'd say it's 50-50. So sometimes it's used twice, sometimes it's not. So don't assume it's going to be used again, okay? But what I want you to do is, again, look inductively. You have the 1 and you have the 3. Basically, how are you getting rid of the 2 and the 4? Because that's essentially what happens. The 2 and the 4 basically disappeared from each side. Well, notice how they're added. The only way to get rid of it then would be to subtract it, correct? So if I were to subtract angle 4, I would have to subtract it from this side. But aren't they the same? See how 4 and 2? So technically what you're doing is you're subtracting the same angle, the same value from each side. So this is the subtraction property. Now notice when we typed this, we put of equality. Again, that is actually the formal name, but if you don't want to put the of equality, I mean, it's just, that's the proper name of it. Sometimes we often drop that, okay? And so that would be our proof. All right, now if you look at number 3, you'll notice there's no linear pairs in this one. So now you're probably going to start to see the other theorem. But again, you have control over pausing the video and trying it by yourself. So I'm going to fill in my given. Remember, you should always get 3 of the points. I don't like to fill in my last statement right away because even though I know this one, sometimes if I write it down, I have a tendency to want to use it. And that's not what I want to do here, okay? So, all right, AB is perpendicular to BC, so they marked it for me. DC is perpendicular to BC, so they marked it for me. Now, it's pretty easy for our eyes to visually look at this and jump to this conclusion. But for these to be equal, we need either their values to be equal, so like they both have to be 45 degrees, or they both have to be 90. We need to actually say the values are 90, or we need to say they're a right angle, because if we look back at our new theorem, we need the word right angle. We need this right piece in our proof. Well, how nice is that? The definition of perpendicular simply says that. The definition of perpendicular says that the lines form a 90-degree or right angle. So I'm going to say angle B is a right angle and angle C is a right angle. Now you could phrase that differently. I'm not saying you have to phrase it the exact same way I did. But if you want to use this new theorem, you need the word right and not 90. Now, let me just kind of quick show you. If you wanted to, for line 2, you could have also said angle B is equal to 90 and angle C is equal to 90. That would have been the same justification. Definition of perpendicular. That would also work. It's the same thing. The only difference here now, when we go to our line 3, because we already know what it is, we already know that they're going to be congruent. On this line 3, you're getting rid of the 90s. So you're getting rid of this and putting C in its place. So you're doing substitution. If you use the word right, This line is still the same because clearly we have to all get to the same point, but now your property is different. If these are right, now we can use the right angle congruence theorem and say if they're right, they must be equal. So if you notice, it's the same number of steps, but your justification pieces might be slightly different. And this is where it is very difficult to say do a Google form document, because there are multiple ways you could fill in the right answer and still be 100% correct, okay? So again, just kind of watch out for that and know that it does exist. All right, we got one more proof here. So again, you are in control. You can pause the video at any given time. Now, this is a pretty long given. So if it's a long given, I will let you cheat and kind of just draw me an arrow. The only thing I caution you on by doing that is if you don't rewrite it, sometimes our eyes have a tendency not to want to use it and we forget about it because it's not like boom, 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 boom. It doesn't fall in a row, or column. So just be careful on that, okay? And also always ask your teacher, because I've had professors that would get mad at you about that and you had to write it in. So you don't want to lose a point for silly stuff like that, okay? All right, it says S is a right angle, and then it says this top one, RTS is 40 and RTU is 50. So it pretty much, it's already marked, all right? Okay, now let's look at this. They want me to prove that angle S is equal to this entire angle. Now, right now, my eyes are adding these together. Like my brain is adding this together and saying, well, it's 90, and so this is 90, so duh, they're equal. But again, you need to lay that out in a proof so it's very organized. So the first piece here, STU, is this whole angle, and what it's telling you is this whole angle is made up of these two parts. So an angle made up of two smaller parts is called angle addition postulate. Now, once again, if you were to mess up the word postulate, let's just say you put theorem, or let's just say you put angle addition, I'd give it to you. But if you really want to, again, be 100% correct, you want to put the word postulate there, okay? Now, this is again where I don't like the fact that we didn't copy this down, because they're using substitution. So clearly something is getting removed here. So if you look, it says RTS. So RTS, which is this same one, notice how the letters are slightly switched. This angle right here is 40. And this angle, notice the letters are slightly switched, is 50. So basically what they're doing is they're switching out the letters for the number, okay? And so now they're saying, well, if this is true, if I substituted these out, then the angle must be right. And the reason is definition of a right angle. Because definition of a right angle tells you you're equal to 90, and this equals 90. Now we know what the last line is. So we already know that. But again, what do we put here? Now, we have used this part of the given up when we used our substitution, and we used this part of the given up when we used our substitution, but we didn't use this. So it's telling us that S is a right, and this other corner is also a right. Well, by our new theorem, if they're both a right angle, then we can say they're congruent to each other. So, right angle congruence theorem. Now, if you don't want to use this, then you would need to probably use substitution. So what you could do is in step of line 4, you could say angle STU is equal to 90, and that would just be by the addition property because you're just simply adding those together. Step 5, you would need to say angle S is a right, or sorry, S is, it already says it's right. I'm using the given right there. S is equal to 90, and that would be by the definition of a right angle. So notice I'm still really using some of the same properties. And then now I would have an extra step, so I would have to add on one step to do my conclusion. So angle S is congruent to STU, and my last step would be substitution. And if you do it this way, notice the substitution property is used twice. Now notice it would not come back to back, so it would be in step 3, and then if you wanted to change the way the proof is written, it would be in step 3 and step 6. Typically, justifications or reasons are not used back to back. Now they can, but it's not very common, so there's a little bit of a gap between that. Okay, so this lesson is a lot about using those new theorems and just practicing more proofs. So it's just practice, practice, practice. The last 2 questions, again, are just trying to get you really to think about mostly linear pair, but some vertical angles and stuff like that. So a number 5, they give you the numbers, and you just kind of have to work your way around the figure, filling in the missing ones. So the easiest ones to start is probably vertical, but this is a straight line. So these 3 right here should total 180. Now that's technically not a linear pair, because a linear pair is only 2 at a time, where this is 3, but we could still kind of use the concept of 180 minus the other angles, and so we get the missing angle right here to be 66. And then notice it's vertical, so this one's 66, this is vertical, so it's 57, and then this is vertical, so it's 57. So you really only had to use that one concept, otherwise it's a lot of vertical angles. Now on number 6, you really kind of have to make a decision here. Now, I'm going to use pencil, and I'm going to use a scrap piece of paper here, because depending on how you would start this, you might run into a problem. So if I was there with you, I would ask you what your thoughts are. And let's just say somebody picks these top 2 angles. If you add these together, you get 180. But you have a problem because you have 2 different variables. Now, I can move the 11 over. I mean, that's not a huge issue, but I'm still going to have 2 variables. So now you're going to be stuck. So if you want to use this, you're going to need to come up with another equation here to do a system. So if I was you, I don't think I would go this route. I think I would try to look for something else. And if you notice in this particular problem, I think vertical angles are going to be your best bet. Now, it doesn't really matter which vertical angle you use. If you go with the ones I just highlighted in yellow, you're going to find the Y value first. If you choose the other diagonal, and I'm just going to kind of put a box around them because this yellow is a little dark, or sorry, orange is a little darker, you find the X. Now, you have to find both, so it really doesn't matter which one you do first. So I'm going to start with the yellow. I would simply put these equal to each other. So if you notice, I'm using vertical angles again. Could I use linear pair? Yes. Would it be harder? Yes. So why make more work for myself? Okay. So then I would solve this. So if I move the 10 over, and then if I divide off the 3, I get my Y value. And then I would kind of, in a way, think of this as a completely separate problem, and I would do the same thing with my X's. So I'm going to go ahead and distribute this. So 4 times X, 4 times 6, and then I set that equal to the other one. And then I'm going to subtract the 4X, and I'm going to subtract the 11. I'm kind of trying to do it at 2 things at a time here. So I get 13. Now you might want to try to plug these numbers back in and just make sure they work, especially maybe try the linear pair. So if we go 13 times 8, So if I do, whoops, I must have hit a wrong key there. Yeah, I hit an extra plus. 13 times 8, I get 104. Now let's plug in the 13 here. So let's go 5 times 13 plus 11, and I get 76. Notice if you add those together, you do get 180. So it works. But again, if you want to use linear pair, I can, but it's going to be a system of equations, and then I'm going to have to pick a method to solve it. So it's just a little bit more work. So sometimes the first thing you try doesn't work. You just got to kind of keep looking around, or sometimes you might just have to use it. It all depends on how it's set, okay? And that concludes chapter 2.